Hi everyone. So today we're doing advanced acid-base equilibria. Our syllabus outcome is calculate and apply dissociation constant Ka and pKa, which is the negative log 10 of Ka, to determine the difference between strong and weak acids. So, some revision from last lesson. Make sure you've done the questions beforehand. Ka is the acid dissociation constant, and it's a measure of how strong an acid is. Kb is the base dissociation constant and is a measure of how strong the base is. And Kw is our water autoionization constant, which is 10 to the negative 14 at 25 degrees, and is the product of the amount of H plus and OH minus in a system. Now, our advanced acid-base equilibria. So today's lesson, it'll allow us to calculate pH of a solution based on the Ka of an acid or base that's been added to the solution. It involves using an ice table with an unknown concentration, and again, always remembering the assumption. Very, very similar to the KEQ questions involving finding concentration. However, we usually have the added step of finding the pH or finding Ka from pKa. So, just a little bit about pKa. Normally, Ka is not the value quoted. The reason for that is the absolute wide range of Ka values. So they can range anywhere from 10 to the power of 5 to 10 to the power of 50. So rather than doing that, we apply the pKa, the P operator to that to get pKa. So it's just a negative log of Ka. Okay. So basically, the higher the number of pKa, the weaker the acid. Now, we can, just like pH, we can find Ka from pKa using 10 to the negative pKa. Now, an example. So, determine the pH of a 1 molar solution of acetic acid, given that the pKa for acetic acid is 4.8. So, what do we have to do? Let's just highlight some of the information that we've got. So we know we have a 1 molar solution of acetic acid, and that's our initial concentration. That's how much we put in. Some of it will dissociate. Now, the amount that dissociates is determined by our pKa, which is 4.8. So basically, we want to find the pH of that. So how do we answer it? Firstly, convert our pKa into Ka. We then determine H plus concentration using an ice table. So just like we've done with all other equilibrium situations. The value can then be used to calculate pH. So there are 3 broad steps, but I'm going to take you through it step by step. So firstly, Ka. We know Ka is 10 to the power of negative pKa. So 10 to the power of negative 4.8 is 1.585 times 10 to the negative 5. Now, our ice table. We know we had 1 mole per liter of acetic acid. That's at the beginning. Okay. We know that some of that is going to dissociate and form acetate and H+. However, the amount that will dissociate, we don't know just yet. Okay. But it's going to go down by X, and because it's 1 to 1, the acetate and the H+ are going to go up by X. Okay. So at equilibrium, we have equilibrium concentrations of 1 minus X, X, and X for that equation. Okay, so now what we need to do is we need to take those unknown values and stick it into our K equation. So we need to solve it for X. We know Ka, products over reactants, so it'll be our ionized products over our unionized reactant. We know acetate and hydroxide ion concentration will be X, and our our acetic acid concentration will be 1 minus X. But we can apply that assumption that if X is much less than Y, Y minus X is approximately equal to Y. So here 1 minus X is going to be approximately equal to 1, because the X is going to be so small that it's not really going to make much difference. So we basically have Ka equals X squared. So X should equal 3.98 times 10 to the negative 3. Now remember, when we take the square root, I know in maths it could be plus or minus, but we can't really add negative concentration to 0. Okay, if there was already some starting concentration of our H plus and our acetate, maybe it would work, but for this one, no, we're just going to take the positive. So we get x equals 3.98 times 10 to the negative 3. Now, as we need to find the pH, we're looking for the concentration of hydrogen ions at equilibrium. So if we look at our ice table, so just have a look back at it, we can see that the equilibrium concentration of H plus is X. So in this case, it's just our X value, so 3.98 times 10 to the negative 3. So we take that value, stick it into our pH calculation, and we get 2.4. Okay, so if we made up a 1 molar solution of acetic acid, it should hopefully give us a pH of 2.4. Okay, so here's another one. Determine the pH of a 0.1 mole per liter solution of formic acid given that the pKa for formic acid is 3.77. Okay. So what we have to do with this one, let's highlight the numbers that we got. So we know it's a 0.1 molar solution. We have been given the pKa of formic acid is 3.77. And yeah, so we need to find that. So firstly, we were given pKa. Again, we need to find the Ka value. So it's 10 to the minus pKa, which is 10 to the negative 3.77, which is 1.698 times 10 to the negative 4. Again, we want to do our ice table for this reaction. So formic acid, we did find the formula for that in one of the earlier lessons we did. Okay, it's just a carboxylic acid with 1 carbon. It reacts and forms formate and H plus. Now we initially start with none of those, but the concentration of the hydrogen ions and the formate ions are going to go up by X. And again, because of the the way reactions work, the reactant side is going to go down if the products go up. So we have X, X, and 0.1 minus X. So solving for X, we need our Ka equation. So we need our COO. Sorry, I've missed a couple of H's there. It should be HCOO minus and H plus, and on the bottom HCOOH. But we know the top ones are X's, the bottom one is 0.1 minus X. We apply our assumption to get rid of that bottom X, and it gives us X times X over 0.1. So we have 1.698 by 10 to the negative 4 equals X squared over 0.1. We solve this algebraically, so we want to get X by itself, so we times both sides by 0.1. which should give us X squared equals 1.698 by 10 to the negative 5. Then take the square root, but remember, only take the positive square root. And again, as we're looking to find pH, we need the concentration of hydrogen ions at equilibrium. So remember, in chemistry, finding X is not always the end of the road. We do have to do things with it. So here, our hydrogen ion concentration, if we look at our ice table, is just equal to X, which is equal to 4.12 by 10 to the negative 3 moles per liter. And then we can find the pH. So the pH should be negative log 10 of the hydrogen ion concentration, which should be negative log 10, 4.12 by 10 to the minus 3, which should be 2.39. Okay. Okay, so for pKb, this is rarely in the HSC, but still good to know because it provides us an alternate method with finding what we need. Okay, it's very similar to Ka. Kb can be quoted as pKb, which is just log 10 of Kb. So the negative log 10 of Kb. And so to find Kb, it's 10 to the negative pKb. Now, pKb questions will generally also involve use of POH. So it's good to refresh yourself on those if you haven't seen them recently. So POH plus pH equals 14, and POH is a negative log 10 of OH minus. And also OH minus is 10 to the power of negative POH. So remember those from a few lessons ago. So we want to determine the pH of a 0.1 molar solution of sodium hypochlorite given the pKb for the hypochlorite ion is ClO minus is 6.48. So we have a 0.1 molar solution, and the pKb for hypochlorite is 6.48. So firstly, we find the Kb, nice and simple, 10 to the negative 6.48, which is 3.31 times 10 to the negative 7. Let's do a ice table. So we know for the reaction of hypochlorite acting as a base with water gives us hypochlorous acid and hydroxide ions. Now we know we put in 0.1 moles per liter of the hypochlorite, and the hypochlorous acid and the hydroxide goes up by X. It's 1 to 1 to 1. And so if we look at that, they go up by X, the hypochlorite goes down by X, and this one down the bottom here, that should be 0.1 minus X. It's not going to matter in the long run once we do the assumption. So doing our Kb, so HOCl times OH minus over OCl minus. So X times X over 0.1 minus X. Apply the assumption, because again, we don't need to use it. Gives us that. And then X squared over 0.1 equals our Kb value. X squared equals 3.311 times 10 to the negative 8. And X equals 1.82 by 10 to the negative 4. So again, we need to find the pH, but we have hydroxide ion concentrations at equilibrium, which is equal to H. So that's our OH minus concentration. POH is negative log 10 of OH, which is negative log 10 of 1.82 by 10 to the negative 4, which equals 3.74 for POH. Now, we want pH, so we're going to have to use 14 minus pH to get our POH value. Sorry, to get our pH value. So we get 10.26. So if we put some sodium hypochlorite into water, it will actually make a basic solution, even though there's no OH in hypochlorite. Okay. Some revision. This is summary. So to calculate concentration of H plus or OH minus at equilibrium, we need to use an ice table. Always use the ice table assumption. Remember, if X is much less than Y, then Y minus X is approximately equal to Y. You also need to use the pH, POH equations for these questions. So they're the ones that are important. Okay, so make sure you do those questions after this, and I will see you next time.